When we're studying the Earth's crust, we often make measurements of features at the Earth's surface, but we're interested in how those features continue down inside the opaque Earth where we can't see them. And we're interested sometimes to calculate the angles between the different kinds of structures that we see. These are spectacular images of structures in Wyoming in the United States, seen in Google Earth imagery, but we often take measurements on the ground when we're doing structural geology in outcrops like these beautiful folds exposed in Nova Scotia in Canada.
In recording the geometries of structures, we often find ourselves wanting to figure out the angle between two structures. Those structures could be two lines in 3D space. Here I have a pen and my Apple Pencil, and I have them arranged so that each one has a different trend and a different plunge, and I wonder what is the angle between those two. Well, we could try and measure it with a protractor, but getting the protractor into the right orientation in 3 dimensions is quite a challenge, and if we're dealing with a real rock outcrop, that may be impossible. A similar problem involves planes. So here's my field notebook. If I open it up, the two covers are planes with different strike and depth, and they may have any orientation in 3D space. So if I want to find the angle between these two planes, once again, with my notebook, I could maybe put a protractor on the end here and measure the angle. But on a real rock outcrop, we probably don't have this surface. So we have to find another way to do it. So the way we have adopted is to use something called a stereographic projection. To show how we do this, I'm going to make a sketch on my iPad. And first I'm going to draw a big field. And we'll imagine our geologist is standing in the middle of the field, and north is this way. And our geologist wants to measure a geologic structure that is plunging down, let's say, sort of towards us and to the right, plunging down towards the southeast. So let's say the trend of this structure is 1, 2, 3 degrees, and the plunge is, let's say, 37 degrees. So it's coming out towards us and plunging down into the ground. So in order to represent this in what's called a stereographic projection, we need to imagine that our geologist is sitting in the middle of a big sphere. Like a giant bubble. And we'll draw the ground here. There it is. And so this big red arrow will be piercing through the sphere, maybe making a little hole in it, somewhere about there. So now we're going to imagine that our geologist climbs up onto the top of the sphere, and that we make a little tiny hole in the top of the sphere, just here, and our geologist looks down through that hole. So let's see what they see. So when we're looking down through that hole, we're going to see a big green circle, which is, if you like, the equator of our sphere. There it is. And we're going to see that red arrow, and it's going to start in the center of our circle, and it's going to head down this way 123 degrees from north. Actually, let's bring it around a little bit, and it's going to go out through the sphere about there, and then down here it will head on further down into the ground. So we can represent the location of that point or that line in 3D space by measuring around from north 123 degrees. That part is easy. And then we need a way to measure somehow 37 degrees down the inside of the sphere. So in order to do that, we need some kind of a protractor measuring device if we're to make measurements on this plan view of the sphere, which is known as a stereographic projection. And if we can find a way to do this systematically, we could maybe plot two lines, or we could find a way to plot planes, and then we can find a way to measure the angles between them. So to show how this is done, I'm going to flip over onto the Visible Geology website, which has a neat stereographic projection tool which helps with visualization.
And you get to this by just typing visiblegeology.com into a browser. And when you click on the StereoNet section, it comes up with this view of the projection sphere, stereographic projection.
So at that point, I see that I'm back to the start, and I have my grid of lines, and I have my little red dot there. So the grid of lines is going to function as a kind of 3D protractor when we do it ourselves. And we do need to be able to do this plotting ourselves rather than relying on Visible Geology to do it for us, because we want to make some calculations and measurements with these points. We don't just want to look at them and say, gee whiz, we plotted the points. We need to be able to do some calculations. So the traditional way to do these calculations was using a sheet of paper with a grid of lines similar to the one that you saw in Visible Geology. So I'm going to flip over now onto the visual presenter, and here you can see what we call a stereographic net, and this is the chart that we are able to use as a three-dimensional protractor in order to make constructions on the stereographic projection. Now, in a traditional class, I would be introducing you to the elements of the stereographic net, which you can see here. And we will do this on the sheet of paper, but you'll meet them again on screen shortly. So you can see the projection is a circle, and the circle is divided up by a whole lot of lines, some of which have names. The first line that's important is this one right around the outside, which is known as the primitive, or sometimes the perimeter of the stereographic net. These lines that go from top to bottom are lines that divide the original sphere in half in 3 dimensions, and those are known as great circles. And that's a term that's used in geography as well to describe lines on the globe. Then we have these lines here, which do not divide the sphere in half. They're all centered on the top and bottom points, and those are described as small circles. The remaining things to know about on the stereographic net are that there are 4 cardinal points here, and we're going to label those top, left, right, and bottom. Notice that we don't label them north, south, east, and west, because one of the things we're going to have to do is to turn this around to make measurements. So they're not going to be in their standard orientation all the time. But they are connected to the center of the net by straight lines. And there are 4 of these, or 2 if you like to think of them as diameters. We call them the 4 straight radii that go out to the top, left, right, and bottom. So you may be wondering what this is for. So in the traditional method, which I'm happy to show people, we would put our thumbtack through the middle of our net, and we would put a sheet of tracing paper over the top, make a little hole in the center, and then we would do our constructions on a sheet of paper sitting on top of the net, using it underneath as our measuring device. That sometimes gets a little confusing, and one of the challenges for beginners using the stereographic projection is that we're always moving around the tracing paper, which is our real-world projection, and keeping our measuring device still because underneath and it's difficult to turn, whereas in the real world, we would ideally do it the other way around. The real world stays still while we move our measuring devices around. Turns out that if we do it digitally, we can avoid that problem and make the process easier.
To carry out these operations on a computer screen, we're going to use a scalable vector graphics file that is .svg. And if we double-click this file, it should open the program Inkscape. So Inkscape is an open source, free vector graphics software, and it's great for constructing diagrams. Works the same way as much more expensive programs like CorelDRAW, Adobe Illustrator, but has the advantage of no cost. And in this program, we've created a wolf net, which is the grid of lines that we need to measure things on a stereographic projection. And one useful thing in Inkscape is to make sure that this palette here, layers and objects, is showing. And then you can see all of the different objects that are contained within the document that you're working on. If that's not showing up, you can get it from this layer menu here, and that will make it appear. So we can select the different objects in our diagram, and one of those objects is down here. It's called the wolf group. And when the object is selected, you'll see these little handles appear at the corners, and we can change those handles by clicking a second time on the object. And then we get what's called a rotation handle here, and if we drag this, we can turn the net around. And you can use the little green numbers at the side, which should stay fixed because they're in a locked layer, and you can use those little numbers to turn the net around to any particular amount you want. So if we wanted to do 123 degrees, we would put it just here. If you want to return the net to the starting position, you can do so. There's a little note at the bottom that gives you the keyboard shortcut in Inkscape: Shift-Alt-T on a Windows machine or Shift-Option-T on a Macintosh. I'll try that now. And if I press that key combination, then the net returns to its starting position. One thing to watch out for is that this wolf group contains a couple of different objects. It has a rectangle and an image inside it. And when you're rotating it, or if you want to return it to its start position, you should make sure that the whole group is selected and not one of its parts. If the net doesn't return into the right position, it's probably because one of its parts has been rotated. So just make sure that stays selected when you're turning the net in the layers palette here over on the right hand side. We have other ways to turn the net around if we want to. So if we go up into the object menu, we can find here down at the bottom that there's a transform option, and that brings another palette up over on the right hand side, and it has sub palettes, if you like, here, tabs, and one of them is rotate. So if I type 1, 2, 3 in here, and then I make sure that clockwise is selected here, because you can do clockwise or counterclockwise here, and I hit apply, it will rotate the net that same 123 degrees that we did by hand before. And once again, if we use Shift-Option-T, we can return it to its starting location. So let's try plotting the orientation of our line with trend 1, 2, 3 and plunge 37 degrees. So here I am in Inkscape, and I'm going to enter in 1, 2, 3 in the angle here. I'm going to apply that rotation, which will turn the net around. And then we've provided here in a layer that's called movable symbols, we've provided a set of symbols. And these are little X's in different colors. And what I'm going to suggest you do is you use the clone capability in Inkscape, which is this icon up here, create clone. And what that will do is it will create a copy of that little cross symbol. The advantage of doing this is that if you decide you want a bigger cross or a different colored cross, you can change the original and all of the copies will change later on. So this is a good way to make multiple objects that are all linked together. So I'm going to get hold of this little cross here, and I'm going to move it down here. So this orientation here at the primitive at 123 degrees, that would be a horizontal line trending 1, 2, 3. So for a plunging line, we have to go down the inside of that sphere, and these are the little lines are 2 degrees apart, and the bold lines are 10 degrees apart. So 10, 20, 30, 36, and 37 is just here. And if you don't think you've got it in quite the right place, you can use the arrow keys to move it around by a tiny amount. And once you feel you have it in the right place, I'm just going to move it up a little bit. There we go. That's done. If you want, we can return the plot to its starting position, and the X will stay put there. My movable symbol is still in the layer of symbols, and it may be a good idea to move it up into the work layer. So I can click on move to layer here, and I can choose the work layer, and I can move my symbol up into the work layer, which was empty before, but that's provided there for you to keep your work. So here we are, we have completed the plotting of our first orientation measurement on a stereographic projection, and that is a line with trend 123 and a plunge of 37 degrees. So how will we go about plotting planes? To illustrate the plotting of planes, I'm using a video captured from the older version of visible geology, which I feel made things a little bit clearer and had a less cluttered screen. So on this older version, just like the new one, you could turn around the projection sphere. And on this version, I'm going to show you how a plane projects on a spherical projection. So here I will go to New Element, Plane. We're going to record the orientation of our planes using the right-hand rule strike and dip convention. Now I know there are other conventions for recording planes, and some of you may use the dip direction dip convention. So we'll try to make another video that explains how to do that. But for now, what you need to know is that the dip direction is 90 degrees clockwise from the strike, the value that we're going to use. And here I'm going to enter a strike, and we're going to make this a strike of 007. And you'll notice that I always enter strikes and record strikes and other azimuth information measured relative to north. I always enter it as a 3-digit number, even if it's a low number like 7. And this helps to keep your observations of azimuths clear and distinct from your observations of inclinations, that is, angles measured relative to horizontal down into the ground. So here we're entering one of those, and we're going to enter in a dip of 42 degrees. So this is a moderately east dipping plane. Now visible geology gives you the option here of plotting but either the plane or its pole or both. And I've chosen both, so I'll show you what that means in the plot. So here we can see the plane, and it is indeed a moderately east dipping plane. And if I turn the sphere around, you can see that there is a stalk coming out of the plane, intersecting the projection sphere on the opposite side of the projection. And this line is known as the pole to the plane. It's the unique line that is precisely perpendicular to the plane. So you can see when we look at a top view, you can see the plane plots as a great circle on the projection, and the pole plots as a dot on the opposite side. We actually use a cross when we're plotting because it's a bit more precise. Let's see how different values of the dip affect the appearance of the plot. So you can see here that gently dipping planes plot as great circles near the primitive, and their poles plot as points close to the center of the projection. Now let's see what happens if we increase the dip to, say, 78 degrees. Here you can see that a steeply dipping plane plots as a great circle near the center of the projection, and its pole plots as a point near the primitive. And the great circle and the pole are always 90 degrees apart, because the pole is defined as the line that is perpendicular to the plane. So let's see how we can go about making this plot in Inkscape. I'm going to select my net here, click on it a second time to get the rotation handles, and I'm going to turn it just 7 degrees. If I want to do this a little more precisely, I'll just return it to the starting position with Shift Option T. I can go into my transform palette here on the right hand side, select rotate, and I can type in 7 degrees, or I can actually click on the plus sign a lot of times, but it's actually easier to just type in 7 here, and I will make sure that clockwise is selected, and I will apply, and there my net is rotated 7 degrees corresponding to the strike direction. So now the next tool I need is this pen tool here, and I'm going to select that, and then there is a series of options up at the top, and actually the default option when you first start up Inkscape is probably this one, but I'm going to choose this one here, which is called the Create Spiro Path, which actually reduces the amount of clicking that we have to do in order to create a great circle. So I'm going to click first at the very top point of the net here, and then I'm going to come over to the right hand side of the net. Now we're plotting by right hand rule, and we've put a little curve here. This is to remind you that great circles, if you're plotting by strike and dip right hand rule, great circles always plot on this side of the net. So my dip was 42 degrees, so I want my great circle to be 42 degrees in from the primitive. There's 20, 30, 40, 42, so that's about there. If you want to make the plot larger while you're doing this, you can press the plus key, and that allows you to zoom it in a little bit to get a little bit more precision. So you click once there at 42 degrees, and as you see, as you drag out the pen, it creates a nice great circle for you, because Inkscape has the capability of fitting a circle through 3 points. So I'm going to click once more at the bottom end of the net, and then I'm going to, as I drag my pencil away, it goes to a crazy shape, but if I right click, then I get my great circle. So one thing that you do need when doing these operations in Inkscape, I think, is a mouse. It's possible to do this all with a trackpad, but it does get quite fiddly at times. So I strongly recommend and require my students to have a real mouse while they're plotting. We can zoom out by pressing the minus key. There we have our great circle. Now, what about the pole? So to position the pole correctly, I'm going to zoom in a little bit so I can get the one that I want, and I can use my mouse wheel to scroll up and down too, which is quite handy. So here is the point that I want, and as we did before when plotting a line, I'm going to create a clone of that so that I keep my original. And I'm going to take my pole over here, and we're going to put it at the central point of the net. And to plot the pole, I need to be 90 degrees away from the plane. So I need to count my 42 degrees out from the center. 10, 20, 30, 42. So there is the position. I can nudge it around with the arrow keys if I want to. I'm pretty happy with that position. Maybe just go a little bit to the right. If you want to adjust your plane, if the plane doesn't come out quite right, there's a node tool here that allows you to get hold of the control points for the plane, and you can move them around individually with the arrow keys. So if your plane hasn't come out quite right, you can move those control points around after you've clicked them, and sometimes that's quite useful if it doesn't land in quite the right place with the mouse. So all these are things you can do to get a nice accurate plot, and usually we hope to have a precision within about 1 degree for our plotting, and a plus or minus 2 degrees for any calculations which we do, which I'm going to show you later on. One final thing we may want to do is to move our objects into the work layer. And in order to do this, it's important to get out of the node selection tool and pick our regular selection tool, so we move the whole objects rather than individual nodes. So I'm going to select my path here, and I will right click on it, and I will move it to the layer, work layer, which is where I want it to be. Let's see where the clone ended up here. Yes, here's the movable symbol. It's called U6 to represent the fact that it's a clone of one of these objects up here at the top. And let's get that into our work layer as well. Move to layer, work layer, move, and there we are. The sample on your screen shows a common combination of structures where we have a planar surface, a fault surface, a slickened side if you like, which has on it a linear feature here, these slicken lines, and those show the direction of movement on the fault surface. So we could measure the orientation of these slicken lines by plunge and trend, but because they lie in a planar surface, it's often convenient to measure them by what we call the rake, sometimes also known as the pitch. So the rake is the angle measured in the surface from a horizontal line. That horizontal line would be the strike. So I'm going to put a compass on the surface here, and I'm going to make sure that that pendulum is hanging directly downwards, and I'm going to draw a strike line on the surface. I need to make sure my compass is touching the rock, and I have a piece of chalk here, so I've drawn a strike line on the surface. Now the rake is most easily measured with a protractor, although you can measure it with a compass as well. And you'll see here, if I put my piece of chalk parallel to the lineation, that the rake of those linear features on the surface is about maybe 140 degrees or thereabouts. So we have a rake of 140 degrees, and the question is, can we convert that into a plunge and trend?
So let's add to our summary diagram an explanation of how we plot a rake. So in order to plot a rake, we have to start from, we'll do this in orange, we have to start from the strike point here, one end of the great circle representing the dip of our plane. Remember that we have to have measured a plane first in order to specify a rake. And we measure the rake along the great circle using those little 2-degree squares on the net. And we'll make this rake quite large, 140 degrees, similar to the one in the video. And then we can plot the location of a point specified by rake within a plane of given strike and dip. And if we want to convert that orientation back to a trend and plunge, then we need to draw a perpendicular out through that point to hit the side of the net here, and that little arrow there represents the trend of our line. And to measure the trend, we need to go all the way around clockwise from north to, there we go. And to determine the plunge, we need to count the number of degrees in from the edge. And that specifies a line by plunge. So without doing any trigonometry, we can convert a line specified by rake in a plane to a line specified by trend and plunge.
Let's now see about plotting this line specified by rake on the projection using Inkscape. So I'm going to select my black X here for the purpose of the line, and I still have the net set up in the position where we plotted the orientation of the plane, 007, 42 to the east. So I'm going to clone my X here, and all I need to do is to take it over here to the right-hand rule strike direction, and I have to count 140 degrees. That was the rake that we were looking at around this great circle. I can actually go quickly because 90 degrees takes me to this straight radius of the net, and then I go 100, 110, 120, 130, 140, and I put the line right there. So there it is. And then if we want to figure out the trend and plunge of that line, we can do it by getting hold of the net here. And there are a number of ways to do this, but for consistency, what I usually do is I take the net and I turn it around. Now it's scrolled off the screen. Sometimes that happens if you drag a little too far. So you can just bring it back if you have a wheel on the mouse. You can just scroll it back, bring it back onto the screen. So what I've done here is to take the top point of the net and to just adjust the direction here so that its straight radius goes through the point that we just located. So now I can read off the trend and the plunge of that line. Its trend looks to be a little over 150 degrees. I would say 155, just shy of there, so 155 to the nearest degree, the trend. And the plunge I can get by just counting degrees down the inside of our projection sphere here, this imaginary bowl, 10, 20, and that looks like 26 degrees. So my line that has a rake of 140 in the plane 00742 to the east has a trend and plunge of 155 and 26. So we're able to convert between a specification by rake in a plane and a specification by trend and plunge.